How Newton could decipher gravity was adequate to allow us to fly from the Earth to the Moon anytime. Get yourself lost in the ticking hands of time, thinking about weather and how we may decipher it. It is basically the tip of the transient chunk of ice on its head. His disclosure isn't just speculation. It's a key that could open the approaches to the secrets of the universe, uncovering a universe more flighty and inspiring than we had ever pondered. Imagine how Brian Cox's new theory challenges our regular comprehension of time, and what are the potential implications for our view of reality. Join us on a captivating exploration through the chronicles of time itself as we dive into Brian Cox's recently revealed, surprising speculation on the nature of time in the vast universe around us. Secrets are ready to be uncovered, and some of these mysteries involve puzzling things like time and gravity, which are central pieces of our world. Imagine a reality where time acts strangely, where it can either slow down or speed up. Furthermore, the force that keeps us on the ground may not be what it seems to be. This is the domain of Albert Einstein's theories of relativity, where our interpretation of time and gravity veers into surprising directions. Albert Einstein, a remarkable name, gave us a superior perspective on the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under different conditions, especially when traveling at incredibly high velocities. It all began in the mid-20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed how we interpret existence. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the possibility of relativistic effects, including the idea that time can stretch or slow down under specific conditions. One captivating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving astonishingly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Here's the fascinating part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. However, because the path is longer for the outside observer, it would seem to take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, isn't just theoretical. Scientists use massive machines like particle accelerators, such as the Large Hadron Collider, to make particles travel almost as fast as light. When things move this fast, we need to think about time differently to make accurate predictions and measurements. Einstein's special theory of relativity changed how we see the universe, especially regarding time and motion. This theory challenges our usual way of thinking. It says the laws of physics are the same for everyone, whether they're moving or not. This differs from our ordinary experience, where we might think adding more speed to a moving object just makes it go faster. However, Einstein's theory says there's a maximum speed that nothing can exceed: the speed of light. From this perspective, events that appear simultaneous to us may not seem that way to people moving near the speed of light. Another outcome of this new way of thinking is length contraction. This means that if something is moving, it appears shorter in the direction it's moving when you observe it from a stationary position. Then, there's the famous equation, E equals mc squared, which comes directly from the special theory. It shows how energy and mass can be converted into each other. This is a big deal for understanding how tiny particles behave when they zoom around at high speeds, as well as for things like nuclear reactions. In real life, special relativity isn't just an abstract theory. It's used in everyday technology like GPS. When GPS satellites send messages to your device, they're moving, so time acts slightly differently for them. If we didn't account for this time dilation effect in our GPS calculations, navigation would be inaccurate. Special relativity teaches us that time isn't the same everywhere. It depends on how things are moving. This idea challenges our understanding of reality. It's like saying our everyday comprehension of the universe is slightly off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some key ideas, like the speed of light always staying the same and the relationship between energy and mass, have been proven through countless experiments. But there's more. Enter Einstein's general theory of relativity, introduced in 1915. This theory dives deeper into the connection between gravity and the structure of the universe. It overturns the old idea that gravity is just a force pulling things from a distance. Instead, it tells us that gravity happens because space-time itself is curved or warped. Imagine space-time as a stretchy fabric. When something heavy like Earth is placed on it, it creates a dent. If you place a smaller object like a ball near Earth, it will roll toward the dent. This is similar to how objects behave due to gravity, not as a mysterious force, but as a response to the bending of space-time. General relativity provides a powerful explanation for how things move in our solar system, like how the planets orbit the sun. It accurately describes the paths planets take, including Earth's elliptical orbit around the sun. This idea differs from the old view of gravity merely pulling things, which struggles to explain planetary motion. Instead, it shows how space-time is curved like a flexible fabric, aligning better with what we observe. A pivotal moment that confirmed general relativity's validity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed close to the sun. According to the theory, the sun's massive gravity would cause the starlight to bend slightly. During the eclipse, these observations matched Einstein's predictions precisely, establishing the credibility of the theory. Just as motion can change how we experience time under special relativity, gravity also influences time under general relativity. In regions with strong gravity, time moves more slowly compared to areas with weaker gravity. For instance, if you stood near a massive object like a black hole, your clock would tick more slowly than one placed far away from such a strong gravitational field. General relativity also introduced the concept of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. The boundary surrounding a black hole is called the event horizon, essentially a point of no return. Once an object crosses this boundary, it is inevitably drawn into the black hole without escape. Einstein's general theory of relativity has far-reaching implications for how we understand the universe. Initially, Einstein added a cosmological constant to his equations because he believed the universe was static. However, when observations revealed that the universe is expanding, he called this assumption a blunder. Yet, this discovery led to a deeper understanding of the universe's origins, forming the foundation for the Big Bang theory. Another remarkable prediction of general relativity is the existence of gravitational waves, ripples in the fabric of space-time caused by massive objects in motion. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected these waves for the first time, confirming yet another aspect of Einstein's theory. These waves are produced by events like the collision of black holes or neutron stars, providing us with new ways to study the cosmos. Over the years, numerous experiments and observations have validated general relativity. Whether it's understanding planetary motion, predicting the paths of light near massive objects, or even the practical functioning of technologies like GPS, Einstein's theories remain central to modern science. They not only challenge but also expand our understanding of time, space, and gravity, painting a picture of a universe that is dynamic, interconnected, and profoundly complex. Twisting of starlight or identifying gravitational waves. The hypothesis has reliably been upheld by proof. While saying gravity is completely wrong might shock many, particularly since we all experience gravity consistently. In the universe of physics, it's not uncommon to discuss and research various ideas. Researchers like Brian often challenge established theories. With gravity, certain individuals question the traditional way we think about this fundamental force. One hypothesis testing regular gravity is called modified Newtonian dynamics, MOND. This theory suggests that gravity acts differently at low speeds, particularly in galaxies, without requiring dark matter. Instead of adding invisible matter, MOND proposes that gravity becomes stronger at low speeds. The gravity debate also involves mysterious dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue these may not be necessary, and alternative ideas could explain what we observe. Some researchers who disagree with Einstein's theory of gravity explore other possibilities, such as theories involving unknown particles or forces that could change or add to our understanding. Science and revolutionary ideas. It's critical to understand that groundbreaking ideas in science are not ignored. They are carefully tested to see if they make sense. For instance, Einstein's idea of time in four-dimensional space, where time travel into the past might be limited by the speed of light, has been creatively explored alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that time travel into the past seems unlikely from a physics perspective. Ongoing experiments and observations test whether new theories can explain phenomena like the strength of gravity while remaining consistent with what we already know. Although alternative ideas have been discussed, none have convincingly replaced the established principles of gravity. Questioning and testing ideas are essential parts of how science learns new things, leading to further research and a better understanding of the universe. General relativity's endurance. In the realm of gravity theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as planetary motion and the bending of light around massive objects. General relativity remains robust because it's straightforward and covers a wide range of phenomena. Einstein's special theory of relativity in space travel. Einstein's special theory of relativity suggests that time can act differently depending on motion. This idea has real-world implications, especially in space travel. Space travel is exciting yet challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This creates a significant challenge for interstellar travel, even with cutting-edge technology, due to the immense time scales involved in reaching the nearest stars. Consider the famous twin paradox to understand what happens with time during space travel. Imagine one twin stays on Earth, while the other travels to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they essentially traveled into the future. Time dilation is critical for space travelers. The longer the journey, the slower time passes for them relative to people on Earth. For example, astronauts traveling to nearby stars could age more slowly than those on Earth. While this might seem like science fiction, it's a real effect predicted by the theory of relativity. Time dilation in technology. Time dilation also affects technology. For example, the Global Positioning System, GPS, relies on precise timing from moving satellites. Since these satellites experience time dilation, it's crucial to account for these effects in GPS calculations. Failing to do so would significantly impact navigation accuracy. The one-way nature of time. Time governs our lives, moving from the past to the present and into the future. This one-way flow of time is fundamental to our existence. But why does time have this one-way nature? To understand, we look at entropy, a concept that measures disorder or randomness in a system. Entropy is linked to the arrow of time and tends to increase over time, causing time to flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or remain constant. In simple terms, entropy naturally increases and doesn't decrease on its own. This explains why things become more disordered over time, such as a shuffled deck of cards or melting ice. Time's direction in physics and the universe. At microscopic levels, the laws of physics allow processes to move forward and backward in time. a concept known as time reversal symmetry. However, the irreversible changes we observe in everyday life arise from the initial conditions of the universe. The universe started in a low-entropy state during the Big Bang and has grown more disordered over billions of years, forming galaxies and stars. Scientists continue to study why the universe began in such an organized state. Even in quantum mechanics, which deals with tiny particles, there's an arrow of time. While particle behavior may seem symmetrical, our observations make changes irreversible. Time travel into the future, a reality? The idea of time dilation, as explained by Einstein's theory of relativity, suggests that time travel into the future could be a reality for space travelers. However, challenges such as long durations, cosmic radiation, and psychological effects make space travel difficult. Time is a crucial aspect of how we experience life and understand our reality. Without its one-way motion, cause and effect would make no sense. Do you think time dilation, as explained by Einstein's theory, could make time travel into the future a practical reality for space explorers? Philosophical implications of time travel and dilation. The possibility of time travel, especially into the future, raises profound philosophical questions. For instance, if time dilation allows astronauts to age more slowly relative to people on Earth, how would societies adapt to such scenarios? Would families endure the emotional toll of being separated by decades or even centuries due to space travel? Moreover, the idea of traveling into the future without returning to the past alters our perception of causality. It forces us to rethink how events unfold and whether choices made in the present could irreversibly affect future generations. In literature and media, time travel often explores these emotional and ethical dilemmas. From works like H.G. Wells's The Time Machine to modern science fiction, humanity's fascination with time underscores its role as a central element in understanding existence. Scientific challenges and advancements. While the theory of relativity lays the groundwork for understanding time dilation, significant technological hurdles remain. Propelling spacecraft at near-light speeds would require unprecedented energy sources and materials capable of withstanding extreme conditions. Current advancements, such as the development of ion propulsion and research into warp drives, aim to address some of these challenges. However, these technologies are in their infancy and far from achieving the velocities necessary for significant time dilation. Additionally, there are biological and psychological effects to consider. Long-term exposure to microgravity, radiation, and isolation can have detrimental effects on astronauts' health. Overcoming these barriers is as crucial as solving the engineering challenges. Practical applications of time dilation. Even if interstellar travel remains a distant dream, the principles of time dilation are already applied in practical technologies like GPS. These applications demonstrate how understanding relativistic effects improves our daily lives, enabling precise navigation, communication, and scientific measurements. Future technologies could further exploit time dilation, such as in creating highly accurate atomic clocks or enhancing space exploration missions. For example, time dilation could provide insights into the aging process and biological adaptation under unique gravitational and temporal conditions. Expanding the boundaries of knowledge. Exploring time dilation and the nature of time itself highlights humanity's relentless curiosity. From Newton's laws of motion to Einstein's relativity, each breakthrough expands our understanding of the universe and our place within it. As researchers delve deeper into quantum mechanics and theories of gravity, they may uncover phenomena that challenge or enhance existing frameworks. Concepts like quantum gravity, string theory, and the multiverse could provide new perspectives on time, space, and reality. The quest to understand time is not merely scientific, but deeply existential. It compels us to question the nature of our existence, the meaning of life, and the possibilities that lie ahead. Conclusion. The one-way motion of time, the effects of relativity, and the potential for time travel encapsulate some of the most fascinating questions in science and philosophy. While many challenges remain, Humanity's pursuit of knowledge and exploration ensures that these mysteries will continue to be explored. As space exploration advances, could we see a future where the effects of time dilation become a routine part of interstellar travel? Perhaps one day, astronauts will not only travel to distant stars, but also experience time in ways that redefine our understanding of existence.